Okay, everyone. Now let's start our lecture 1, part 2. So from last lecture, we have introduced some concepts of charges, and we also introduced the basic unit of charges in atoms. So here shows a picture of atom, and we have learned that an atom is composed by two types of elements, let's say electrons and the nucleus. And the electrons are negatively charged. They're surrounding the nucleus. The nucleus is positively charged. Compared to the size of the atom, the nucleus is very small, and the nucleus contains both protons and neutrons. So protons or neutrons are smaller elements which are the components of the nucleus. And the difference between protons and neutrons is that the neutrons doesn't have any charges. As its name shows, it's neutral. So that's why it's called neutrons. And for protons, they are positively charged. So the reason we can say that the reason why the nucleus is positively charged is because of the protons. The proton is positively charged. That's why. Okay, next. So here it shows some, oh, go back. So here shows some, let's say numbers or details about proton and electron. So the atom is held together by the attractive force between positively charged nucleus and the negatively charged electrons. The electrons and the protons have charges of opposite sign, but exactly equal in magnitude. So if we look at the previous picture, we'll see if there are five, let's say five positively charged or five protons in the nucleus, then there should be five negatively charged elements, which are electrons surrounding the nucleus. So the entire atom is neutral. So that's why it says electrons and the protons, they have exactly the same numbers in the atom. This atom or atomic level unit of charge is called fundamental unit of charge. Usually we use E as a symbol of fundamental unit of charge. We say a proton has a unit charge, or the proton has a charge of plus E or positive E, and the electron is one electron is charged by one negative E charge. And E is the smallest charge. So you will never find a charge which is smaller than E. And later on, we'll learn the magnitude of E. And if we compare proton and the electron, we'll see the mass between them is significantly different. So for electron, it's 9 times 10 to the power negative 31, or 1 times something surrounding like 1 times 10 to the power negative 30. So it's 1,000 heavier. Sorry, the proton is 1,000 heavier than atom. Or the electron's mass is only 1/1000th of proton. So if you compare proton and electron based on their mass, the mass of electron can be ignored because it's too small compared to protons. But they have the same magnitude of charge. However, the sign are opposite. The electron has negative, but the proton has positive signs. Now let's quantitatively introducing the charge or the magnitude of charge for proton and electron. So first of all, a macroscopic object has net charge of Q equals to n positive times E subtracted by n negative subtracted by E. So here, NP and E means the number of positively charged elements or the number of protons. E means, Ne means the number of electrons. So the total number of protons subtracted by the total number of electrons times the electric unit or the charge unit, then you have the total charge of your object or your material. So most microscopic objects have equal number of protons and electrons. Therefore, it is neutral for such an object. And then the net charge Q is 0. A charged object has unequal number of protons and electrons. Notice that an object charge is always integer of E. This is called charge quantization. The process of removing an electron from the electron cloud of an atom or adding an electron to it is called ionization. So for example, in previous example, we have saw one atom which is composed by 5 protons and 5 electrons. However, what happens if one electron is missing in the electron cloud? Now you will have 5 protons, but 4 electrons. Then this atom becomes no longer a neutral atom. It becomes an ion. Ion is something, is an uneven charged atom. It either gained some extra electrons or it loses some electrons from a neutral atom. When it gains electrons or loss electrons, then it becomes ion. So here is a positive ion, means the proton number is bigger or greater than electron number. In the opposite way, you will see negative ion. Negative ion has more electron than proton. So that's why they become positive or negative. That's uneven number between protons and electrons in ions. Okay, so now let's see the molecular ions. Molecular ions can be created when one of the bonds in a large molecule is broken. For example, now you have a molecule which is composed by 1, 2, 3, 4, 5 atoms. Those springs between the beads demonstrate the bonds between atoms. So for some reason, for example, either heat or some chemical reasons, or some other reasons, some collision or something happened to the molecule, there might be a chance that the molecule is broken into 2. For example, here and there. When it breaks, it's possible that the 2 parts may not be neutral anymore. One part may be positive, the other part might be negative. Then this is called positive molecular ion and negative molecular ion. So this is a way in which a plastic rod is charged by rubbing with wool, or a comb is charged by passing through your hair. Simply, when let's say we're scratching a plastic on the wool, actually there are a lot of molecules has been broken, and the broken parts might have positive charges and negative charges. So the negative charges likes to stay on the plastic rod, and the positive charged part of the molecules prefer to stay on the wool. Then your plastic rod becomes more negatively charged. So that's the reason for our previous experiment. Okay, once we understand the electrons, protons, ions, and molecular ions, then let's introduce the mechanisms for insulators and conductors. So first, insulators. The electrons in the insulator are all tightly bound to the positive nuclei, and they're not free to move around. So charging an insulator by friction leaves patches of molecule or molecular ions on the surface, but these patches are immobile. For example, this is a, let's say, insulator. Let me get my pen to make some pictures. Let's say this is the insulator, and you have nucleus and electrons. Those electrons are always tightly bound to the nucleus, so they cannot move freely. So by some reason, even you break some molecules in the insulator, so that you get some, let's say, positively charged molecules at the surface, then those positively charged ions, when or molecular ions, they are not mobile, so they cannot move to other part of the insulator. Or for some reason, if you charge them by negative charge, then the negative charges, they are still not allowed to move, or the electrons are not allowed to move in insulators due to the structure of the insulators. So that's why for insulators, even you charge it on the surface, the charge doesn't move. It stays on the surface. For the other part, it keeps neutral. Now let's see conductors. In conductors, such as metals, the outer atomic electrons are only weakly bound to the nuclei. What does that mean? That means the electrons are free. It's like cloud in the entire material. So they can move freely. These outer electrons become detached from their parent nuclei and are free to wander about through the entire solid. This solid as a whole remains electrically neutral, but the electrons are now like a negatively charged liquid permitting an array of positively charged ion cores. Now, from this picture, you can see those are the nuclear cores, and the dark green means some tightly bound, let's say, electrons, and the light blue means the free electrons. So the electrons are freely moved from one place to another place. Therefore, if the, let's say, the metal is charged here, or let's make it a negatively charged, which makes it easier. Let me get my eraser. Where is the eraser? Okay. And pen. Pen. Okay. Where's my pen? pen. Okay, no, that's my pen. For example, if you get some charges on the surface of the metal or conductor, let's say negatively charged, those negatively charges are freely moving inside the conductor. So they will move around in the conductor. And then we'll see if there are some free charges, like negative charges, what will happen? What's the distribution of those charges in the metal? So actually, they will be distributed on the surface, on all of the surface of the metal. And we'll introduce why in later slides. Now let's introduce another, let's say, concept, which is charging. So this figure shows how a conductor is charged by contact with a charged plastic rod. So for example, you have a plastic rod with negative charges. If you touch the negative charge a rod on the surface of the metal, then let's say negative charges will be easily transferred in the metal or conductor. This is called charging. And then, as we said, the charges or electrons in the, let's say, conductor or metal, they're free. So what happens if you move away your rod and let it have some time, then you will see all of the charges will be distributed on the surface of the metal. Why they're on the surface? Because there are repelling forces between each two of the negative charges. So they're repelling each other. So they're trying to get as far as possible with each other. So they will be distributed on the surface of the metal. Discharging. So here shows a process of discharging. Now, if you have a metal, and then let's say if a man is touching the metal, what happens? So first of all, we need to understand that a human body is also a conductor. So what happens is conductor contact with another conductor, those two conductors become, let's say, a whole piece of bigger conductor. And then the charges are moving freely in the big piece of a conductor. They try to repel each other, then they will be distributed on the surface of the entire conductor, including the original piece of conductor and the human body conductor. If your human body is much bigger than the piece of conductor, then most of the charges will be distributed on the human body. Only a little bit charge will be left on the original conductor. That's why in our previous experiment, actually in last lecture, we see this when you touch a piece of charged conductor, then the conductor become neutral because the human body take away most of the charges. Okay, now here shows the let's say charge polarization. So let's say now if you have a positively charged rod in hand, and then you have a neutral device like that. This neutral device, let's say, has a head, or this electroscope has a bead on the top, and then it has two leaves on the bottom, and they are connected by a conductor rod. So what happens if you put a charged, no matter it's positive or negative charged rod close to the bead or head of the electroscope? What will happen? Let's take positive charged rod as example. If it's a positively charged, then what happens is at the beginning, the entire electroscope is neutral. However, it's a conductor. So the electrons are freely moving in the conductor. This is a positive charge, and the positively charged rod will attract more negative charge. So the negative charge trying to come to the tip of the head, and the positive charges are repelled by this rod, and they prefer to stay on the leaves. And then the two leaves are all charged by positively charged charges, and then they will repel each other, and then these two leaves will open. So this is called charge polarization. If you remember, we can use a charged, no matter it's a positive or negatively charged rod, to pick up small pieces of object, such as small pieces of paper, even the paper is neutral. So why? The reason is similar. When you have a positively charged rod close to a neutral object, then the negatively charged charges, the negative charges will be attracted by your positive charges on your rod, and the positively charged particles are repelled by your rod. And then you will have the charge on the small object distributed like that. Negative on top, positive on bottom. Then what happens is, due to this distribution, or we call it, this is a polarized piece of object. Due to the distribution of the charges, you will see the attractive force becomes bigger, and the repelling force is smaller, because the distance between negative charge and the positive charge is closer or shorter, and the positive charge to positive charge is longer. So the attractive force is bigger and the repelling force is smaller, and then the net force is going up. So that's why you can use a charged rod to pick up or attract some neutral pieces of object. Okay. The electric dipole. So this figure shows how a neutral atom is polarized by external charge. For example, if you put an external charge, which is a positive charge here, when it's close to an atom, the negative charge will be attracted by the external charge, and the nucleus or positive charge will be repelled, and then they will be separated, and then you have the atom polarized. You have a negative side and a positive side. Similarly, you will have the force between positive charge and negative charge greater than the force between positive charge and positive charge. Then the net force will be attractive force, which is similar to the small piece of object. And if you have a, let's say, strong external charge, and you have an insulator, you will similarly have a net force, which is attractive force. Why? Because you can consider that this insulator is composed by many atoms. So each atom is polarized in this way. It's a neutral atom, but the neutral atom has been polarized to be more negative on one side and more positive on the other side. If there are a lot of atoms behaved in this way, then if you sum up all of the polarized atoms effect, then you will see the net force between the external charge and the whole material is still attractive force. Okay, here shows one interesting experiment. So first of all, as we discussed, let's use a positively charged rod to get closer to the electroscope. And then the head of the electroscope will be negatively charged and the tails or the leaves will be positive. And then keep it like that, but if there's a human body touching the head of the electroscope, what will happen? Similarly to, let's say, similarly to the conductor. So we'll have negative charges surrounding the hand, but positive charges on the other side of the human body. And those negative charges are distributed on this area. Now the entire human body and the, let's say, conductor is a whole piece. Then for this whole piece, the negative charges are mainly distributed to the areas which is the most closed to the rod. And then in this case, it's mostly on the sphere. And then what happens is, if you take away your hand, get away from the this device or this set of experiments, you will see there are a lot of negatively charges on the sphere, but only fewer positive charges on the leaves. And then this device becomes now if you take away all of the external devices like the rod and the human body, then what happens is the whole device is charged by negative charges. So that's an interesting experiment. So let's say the positively charged rod attracted the electrons from human body and the electroscope. However, because it's closer to the electroscope, so more negative charges are located on the electroscope. So when you take away the human first and then take away the rod, then this device is negatively charged. Okay, that's an interesting experiment. If possible, if it can be done in the lab, I highly encourage you to do similar things in the lab and see if it works. So here are some questions. You have questions and answers in the slides. I think you don't have any problems with solving those questions. If you have, just send me an email or make an appointment with me and we can discuss. Okay, so from now, we're going to introduce an important equation, which is Coulomb's law. So Coulomb's law is an equation to calculate, quantitatively calculates the magnitude between charges and also indicates the direction of the forces between two charges. So when two positively charged particles are in a distance of r, they each experience a repulsive force, which is shown in this figure. And based on Coulomb's law, the magnitude of the forces between Q1 and Q2 can be calculated by K times Q1, Q2 over R squared. Q1, Q2 are the charges on the charge 1 and charge 2. R is a distance, K is constant. In SI unit, K equals to this number. So once you learn Coulomb's equation, then you can always calculate the force between two charges. Similarly, if there are two negative charges, the equation is the same and the direction of the forces are still repulsive. However, if the two charges are one negative and one positive, then the equation for the magnitude is the same, but the direction becomes opposite. They attract each other. So that's the entire definition of Coulomb's law. It gives you the equation to calculate the magnitude and also tell you the direction of the forces between two charges. Okay, so here are some questions. Well, I think you don't have any, you won't be having any troubles with those quick check questions. Usually in the slides, the quick check questions are relatively easy. Again, if you have any questions about those quick check questions, if you have problem with the answers, please let me know. Now, let's talk about some more details about the Coulomb's law. In Coulomb's law, we have a constant, which is K. Actually, this K could be interesting. It could be different in different materials. Let's introduce another concept for material, the permittivity constant. So permittivity constant sometimes is called dielectric constant. It's a constant for a material. Different material have different dielectric constant or permittivity. So we can make many future equations easier if we rewrite Coulomb's law in a more complicated way. Actually, it's not complicated. Don't be afraid. Let's see. If we define a new constant, which is permittivity constant or dielectric constant, epsilon, then this epsilon is defined to be 1 over 4 pi k. K is the constant we introduced in the Coulomb's law. And then we can rewrite Coulomb's law in terms of epsilon, which will be 1 over 4 pi epsilon, which is just the k. K equals to 1 over 4 pi epsilon, and times Q1, Q2 over R squared. And be careful that epsilon 0 means the dielectric constant or permittivity in vacuum or in gas. If you're trying to calculate the forces using Coulomb's law in different materials, such as in water or in other materials, then epsilon 0 is a different constant. Actually, not epsilon 0. If you calculate the forces in different material like water, you will need adjustment of this epsilon 0, and then we'll introduce another epsilon, which is, let's say, epsilon material. Let's say epsilon W, indicating the epsilon in water. So you will use epsilon water to calculate the force based on Coulomb's law in the material of water. But here, by default, we're talking about the forces in vacuum or in the air. Then you can use epsilon 0. Okay, problem solving strategy. Okay, how to solve problems by using Coulomb's law. You just need to first recognize if there are positive or negative charges, or are they positive plus, or are they one positive charge with one negative charge, to determine what's the direction of the forces. And then you use Coulomb's law to calculate the magnitude. So that's very easy. Let's take an example here. A small plastic sphere charged to -10 NC, which is a unit we introduced in previous slides. It's held 1 centimeter above a small glass bead at rest on a table. The bead has a mass of 15 milligram and then a charge of positively 10 NC. Will the glass bead leap up to the plastic sphere? Okay. If we draw a picture, we can show it here. So you have a glass bead on the table. You have plastic charged particle above it. The distance between them is 1 centimeter or 0.01 meter. Because when you're using Coulomb's law, you have to convert it into SI unit first, which is in meter. And of course, you have the charge here. So you also have a charge for Q2 here. So first, let's calculate the charge of the force between Q1 and Q2. And then let's calculate the, let's say, gravitative force on the glass bead. Then let's do a comparison. If the electrostatic force or the attractive force is greater than its weight or the gravitative force, then it will leap up or it will be attracted. If not, if the gravitative force is greater, then it will stay on the table, of course. Then let's calculate both of the force. First of all, the electrostatic force, we'll use Coulomb's law. We take K and then Q1, Q2, R squared into the equation, you can get the number. And then let's calculate the weight or gravitative force. I guess all of you have learned how to do the calculation in your previous lectures. So the weight equals to mg. G is a gravitativity constant. So m is the mass of your glass bead in this example. And then the number is shown here. So obviously, the electrostatic force is much greater than the weight. Then the speed will go upward. So that's the way of solving this problem. The only difficulty is using Coulomb's law to calculate the equation. So plug in all the numbers and calculate the final number. Do a comparison between this number and its weight. That's the process of solving the equation. Okay, so let's stop here. We have introduced the most important concept, which is Coulomb's law. In next class, we're going to introduce another concept, which is field. Okay, thank you, everyone. I'll see you in next lecture.